The first lecture is going to be on complex numbers. The first thing I want to do is do a little bit of revision of the Maclaurin series stuff. So first question here is, show that the Maclaurin series down to the x to the power of 6 term for cos x is 1 take away x squared over 2 plus x to the power of 4 over 24 take away x to the power of 6 over 720. And then it says, hence find the Maclaurin series for cos 2x. Then part C, obviously all these questions follow on from each other. Find the integral between 0 and 1 of x squared cos 2x dx. So pause the video here, take a note of the questions and try it for yourself. Okay, so I'm just going to put the answers up now. This slideshow or software is something that I've done already with the HND electrical engineering class. So the majority of it's revision, so I'm not going to be writing that much. I'm just going to be showing you and talking you through things. You've done complex numbers already in Engineering 1. There's not a lot that's different. It's a little bit on exponential form of a complex number and de Moivre's theorem, which is different. The rest is the same. So I'm hoping we'll get through the majority of complex numbers really quickly. Right, so let's start with this. So it's a Maclaurin series. So we put our two headings, and our two headings are, we've got our derivatives, and over here we've got our coefficients. Okay, so start with f of x is cos x. So f of 0, because Maclaurin means x equals 0, equals cos 0, which is 1. And this is the most standard Maclaurin series. It's either going to ask you sin, cos, or exponential. That's all it can really ask you. So that becomes negative sin x. So f dashed of 0 is negative sine 0, which is 0. Okay, then f double dashed of x is negative cos x. So f double dashed of 0 is negative cos 0, which is negative 1. Remember, I want to go down to the x to the power of 6 term, which means I need to do 6 derivatives. All you're doing in this is you're showing that you understand where Maclaurin series come from. Okay, because in the majority of the time, if you were doing a question involving Maclaurin series or Taylor series, you would just... Software is annoying. It keeps on getting rid of horizontal lines. Right, then the fourth derivative of x is cos x, which means the fourth derivative at 0 is cos 0, which is 1. Fifth derivative is negative sine x, which means that the fifth derivative at 0 is negative sine 0, which is of course 0. And lastly, the sixth derivative at x is negative cos x. So the sixth derivative at 0 is negative cos 0, which is 1. I'm sorry, negative 1. Right, so then we say f of x is equal to f of 0 plus f dashed of 0 x over 1 factorial plus f double dashed of 0 x squared over 2 factorial plus f triple dashed of 0 x cubed over 3 factorial plus the fourth derivative 0 x to the power of 4 over 4 factorial, and so on. So you get two terms left, the fifth derivative at 0, x to the power of 5 over 5 factorial, and the sixth derivative when x equals 0 of x to the power of 6 over 6 factorial. So that's what you've got to go for. Right? And remember, all we're doing is we're swapping these coefficients here in place of incorrect place. Now that's that wee dash is not in there. Right. Okay, so f of 0 is 1. So that means that f dash of 0 is 1 plus 0x over 1 factorial plus negative 1x squared. 2 factorial is 2 plus 0x cubed over 6 plus 1 x to the power of 4 over 24 plus 0 x to the power of 5 over 5 factorial, and 5 factorial is 120 plus negative 1 x to the power of 6 over 6 factorial, which is 720. So you can work out your factorials at any point. It's not an issue. You just do it if and when you want to, right? And remember, you're told what the answer should be, so it should hopefully work out for us. So that means that f of x is equal to 1 take away x squared over 2 plus x to the power of 4 over 24 take away x to the power of 6 over 720. And there we go. That's me got that answer that I was looking for in part A of the question. Right, now, as I said, this is something I've done before, so I'm just going to run through how we did the next bit. So part B, hence find the Maclaurin series for cos 2x. So cos x is what I've worked out in part A. So this bit here from part A. And all we do is, because it's 2x in place of x, we're just going to put 2x in a bracket wherever we see x in the normal expansion of cos x. Now, key thing here, that when you square out the brackets, or the power of 4 to the power of 6, you need to do the number and the letter. So 2 squared is 4 and x squared is x squared. 2 to the power of 4 is 16 and x to the power of 4 is x to the power of 4. 2 to the power of 6 is 64 and you get x to the power of 6. Then all you need to do is, once you've done that, you just simplify your fractions if you can. And if you want, you can just type 4 over 2 into your calculator, 16 over 24 into your calculator, and 64 over 720 just to make sure. Because remember, if you've got a calculator, you may as well make sure that your fraction work is correct. Now, let's go on to the next bit then. So the next bit is C was, hence integrate this thing here. Now, I've already got an expansion for cos 2x. So that's going to make it easier, because if I have to do this question here, I'm going to probably have to use integration by parts. And although integration by parts is relatively straightforward, it's a wee bit longer, bearing in mind we've already worked out what cos 2x is. So I put cos 2x in here, and we're multiplying that by x squared. And all we're doing is we're multiplying through everything by x squared till we get here. Now, the most common thing people will forget to do is actually integrate the question. So they'll get to this line here, they'll swap the brackets over, but they won't actually integrate your x squared. Integrate this thing here. So remember, integrate, increase the power by 1, divide by the new power. Increase the power by 1, divide by the new power. Increase the power by 1, divide by the new power. All the way along. And remember, your integral sign in dx becomes a square bracket with the limits moving over to the other side. That's so that you can tell the marker, I've actually integrated here and I know what I'm talking about. Right, then what we do is, when we substitute in our limits, we put in the first one and then take away the second one. Well, this second one was just clearly going to become 0, and the first one, I've just typed all that into a calculator the way it is, and I've got 0.0. units. So you'll be asked to do something very similar to this in any assignment you would get in this unit. So make sure that you have a little look, make sure you know what you're doing, make sure you integrate is the key thing that we're looking to do. Right, so that's the whole of that revision question. Be ready for something like that. Right, so as I said, this next stuff is stuff that we've all done before in Engineering 1. So we did it at the start of the year. So it's all to do with complex numbers. Now, real numbers, we use real, and we normally say that x is an element of the real numbers. Now, complex numbers are used to solve problems that involve finding the square root of a negative number. So if you're looking to find the square root of -9, we can't do that if we're talking about real numbers, because there's no real number that allows that to happen. Okay? So in complex numbers, we can, as long as it says this, x is an element of the complex numbers. Right, so that is the key message. It's all about finding the square root of a negative number. So, example number 1, solve this equation here. Now, it says x is an element of the complex numbers. It's that good, so that means that we can use that information. Right, so that can't be factorised. If we tried our wee add to make +2 and multiply to make +5, that's impossible. So it's impossible to factorise that equation. So that means we need to use the quadratic formula. And the quadratic formula is something that we've been using all the way through our maths life since we did National 5. So this is our quadratic formula, and we left off our 1, our 2 and our 5, and we substitute it into the formula. Now remember, don't just type it all into the calculator like that, because we're going to get issues here. It's going to give you an MA error if you type that in one go, because the calculator only deals in real numbers. It doesn't deal in complex numbers unless we tell it to work in complex numbers, and that's not something that we do. Right, so we always simplify this bit here if we can. We simplify under the bracket, under the square root if we can, so that's how we got -16, and we simplify the bottom if we can. Now this is our issue here, right? This is our issue that we would have if we were using the real numbers rather than the complex numbers. We would just say that's impossible. But what we do is the negative sign we can effectively swap in for j squared, because j squared is the same as -1. You might also see that as I squared. They tend to use I in maths and j in engineering. Depends who your lecturer is when you go into uni, depends on what letter they decide to use. Right, so you make that j squared 16. Now all we need to then do is find the square root of this thing here. So the square root of j squared is j, and the square root of 16 is 4. Then all I've done is we'll just ignore this wee bit here, because that's just my ramblings from before. Right, and then all we do is we just split it down the middle on the top of the fraction, and we divide the two bits. And we're left with two answers, -1 plus j2 and -1 take away j2. Now, it might be that you get to a stage and it's a horrible decimal somewhere in here. So you might get 3 plus or minus the square root of j squared 87 over 5. Let's say that's what you do. So you would then write that as 3 plus or minus j. Now what you could either write here is write the square root of 87, or you could just type that into your calculator, the square root of 87 as 9.372. So I would work to 4 decimal places if I was doing that. So I would write 9.2, sorry, mistake, 9.3274. over 5. And then I just split the two bits. So I would do 3 over 5 plus or minus j 9.3274 over 5. And then just divide them in my calculator. So that would be 0.6 plus or minus j 1.865. So I'm just saying that you're not always going to get lovely whole numbers like here. If you end up with something dodgy, just make sure you square root the j squared to give you j and square root that number there. And decimals are absolutely fine, as I've said. We know that trying to keep things in square roots makes the answer more accurate because there's no rounding involved, but at the end of the day, if you're using 4 decimal places, you're accurate enough. Okay, so that's just a wee additional ramble from me. Right, now, if we remember from Engineering 1, a complex number you can draw a wee diagram of, and it's just like a wee vector diagram. So these are my two answers. Let's say that's x1, that's x2. Right, so if I'm drawing this, that means it's -1 along and 2 up in the imaginary way. So that is my complex number there. X1 is just given by that line there. Okay, because you've had to go 1 along the -1 along the real axis and 2 up the imaginary axis. Same here, we're going -1 along the real axis, but this time we're going 2 down the imaginary axis. That means this is my complex number here, x2. So remember, this bit here tells you how far along the way it is, or how real the number is, and the j part tells you how imaginary the number is. Okay, so that's how you find a complex number, or how you would solve an equation that would give you a complex number as an answer. Right, now you're going to have to be able to add, subtract, multiply, and multiply a complex number by a scalar to start off with. So what I've done here is I've given you 3 complex numbers. Okay, sorry, 4 complex numbers, I can't count today. And I've given you 3 questions on them. So first one, we want to add z1 and z3. Second one, we want to do 4 times z2, take away 2 times z3. And then lastly, 3 times z3 plus 4 times z4. So z1 plus z3, dead easy. You add the real parts, gives me 11. You add the imaginary parts, that's 6 plus -4, which gives me 2. That just gives me 11 plus j2. Simple as that. You add the real parts, you add the imaginary parts, and see what happens. Right, if we're multiplying by a scalar, first thing we do is we multiply each part of the complex number. So I've multiplied that bit by 4. So I've just taken z2, which is this number here, and I've multiplied both parts of it by 4. Then I'm taking away 2z3, so I've taken z3 and just multiplied everything there by 2 to get this number here. And then all it's telling me to do is take these numbers away from each other. So I'm going to subtract the real parts. So -40 take away 16 is -56. And -32 take away -8, so that becomes +8 is -24. So 4z2 take away 2z3 is -56. Take away j24. And we've done that already. Same with this one here. You multiply z3 by 3. You multiply z4 by 4. And then you add the two answers together. So there, multiplied z3 by 3. Multiplied z4 by 4. And I've just added the real parts. And then added the imaginary parts. Now if you look at worksheet 1, on complex numbers, question 3 is a whole lot of questions like that, but that should be stuff they've already done and we shouldn't have to look at in too much detail. Alright, next stuff is multiplying complex numbers. Now this is just multiplying out brackets with a wee twist at the end. So we write our so I've got 2 complex numbers here. So the first step is we write our numbers side by side in brackets. Okay, our second step is we expand the brackets, and step 3 is we stop j squared for -1. And I suppose step 4 is you simplify and collect like terms if you can. But the whole way through any question involving algebra or brackets and anything like that, you should be simplifying as you go along anyway, because that's what we've been doing all the way through. So, example number 1. So Z1 is 3 take away J8. Z2 is -4 take away J9. And what I want to do is do Z1 multiplied by Z2. Because remember, if there's nothing between two things, it means we have to multiply them. So, step 1, you write the two complex numbers in brackets, side by side, just like you'd imagine. And then we just multiply out the brackets. I always put the j at the start. So 3 times -4 is -12. 3 times -j9 is -j27. -j8 multiplied by -4 is plus j32. And -j8 multiplied by -j9, that gives us positive j squared 72. Right, so you've just multiplied out your bracket like you normally would. Now, as always, pretty much you can simplify your middle terms. So -j27 plus j32 is j5. Right, so that's me. I've multiplied out my brackets, I've collected my like terms, everything's all good. But remember that j squared is -1. So all you need to do here is always just change, if there's a j squared there, just change that sign. If it's a positive, it becomes a takeaway. If it's a takeaway, it becomes a plus. Whatever you want to think about it as. Or you can just show the working by substituting in the -1. Whatever you are more comfortable with. Okay, so then what we can do is we can collect the -12 and the -72 together, and we get -84 plus j5. And that means now you're able to do questions 1 and 3 on worksheet 2. So as I said, that should just be you going through and remembering how to do these. It shouldn't be anything that's particularly new to you. Right. Now, the next thing relies, so if you want to pause the video here and try those questions, I'm going to go and talk about the next thing, and that's complex conjugates. Now, complex conjugates are really important because these help us divide complex numbers. So, a complex conjugate is basically all that happens is the complex bit changes sign. So if this here was your original complex number, its complex conjugate is this thing here, because it's got the opposite sign in front of the complex part. Now, if you multiply out a complex number multiplied by its complex conjugate, you always get the first number squared plus the second number squared. And here's a working to prove it. So 2 times 2 is 4. 2 times -j4 is -j8. Positive j4 plus 2 is j8. So these two bits will always cancel out every time. These bits will always cancel out, leaving us with j to the power of j4 multiplied by -j4, which gives me -j squared 16. We know that this here changes to a plus, so that's why it's always the first squared plus the second squared, just like I've put here. And that makes dividing by complex numbers a little bit easier, right? Let's do the same again, right? If this time 5 take away j3 was my original complex number, right? This would be its complex conjugate, because I've swapped the negative or the takeaway sign for an add sign. Now, you multiply out the brackets as normal. Same thing happens. Your middle terms always cancel out. You're left with j squared 9 and the take away j squared becomes a plus. So again, that's 5 squared plus 3 squared, which is the first squared plus the second squared. So if you multiply a complex number by its complex conjugate, which means you change the sign in the middle, it's always the first number squared plus the second number squared, or the real part squared plus the imaginary part squared. Right, you might think, what's the point in me doing that? It's all to do with dividing complex numbers. Okay, so I think it's going to be easier for me to actually do this in pen rather than just running through it. Now, there's a reason why I'm going through this. Right, so you've got 2 take away j5 over 3 plus j4. Right, now, I know from maths that I should never have a complex or some horrible term on the bottom of a fraction, right? Now, what we do is we multiply the top and the bottom by the complex conjugate of the bottom. That would be the complex conjugate of the bottom over the complex conjugate of the bottom. Because that doesn't change the number, because that's just the same as multiplying it by 1. But it makes everything come together and it makes everything nicer. So you multiply top and bottom by the complex conjugate of okay, right. So we just multiply out the brackets. So what I'll do is I'll just write them next to each other. Right. Oops. Right. See, software's been dodgy again. Right. So we just multiply everything together. So we're going to do 2 multiplied by 3, 2 multiplied by j4. That multiplied by that, and that multiplied by that to expand my brackets, right? So that's going to give me 6, take away j8, take away j15 plus j squared 20 all over. Now, this bit here is the complex number times its complex conjugate. So remember, that just becomes the first squared plus the second squared. That's why I did that in that last slide. So that's just going to be 3 squared plus 4 squared. Or you can multiply out those brackets the same way, but it's just going to take you a wee bit longer. So that's 6 take away j23 plus, I'm just going to show you all the working, and then that bottom bit is just 25. Just like that, right? Right, so then here, remember, because j squared is -1, that becomes take away 20. That gives me -14 take away j23 over 25. Split it in the middle. And that's you Done. That's you divided a complex number by using the complex conjugate. As I said, that is 100% necessary knowledge for you. Okay, so back up to the top. So you get a complex number, you've asked to divide it, so that could be Z1, that could be Z2. You asked to divide them, so you set them up like this. So then you have to multiply the top and the bottom by the complex conjugate of the bottom. Then you multiply out the brackets in the top. If you remember the shortcut for the bottom, which is the first squared plus the second squared, and you simplify everything down and you get to this thing here. Another reason that I'm staying away from writing as much as I have been is because these negative signs keep on disappearing, these lines keep disappearing, so all my adds and my subtracts keep on changing, and it means I mess stuff up even more than normal, so I'm trying to avoid doing that. Right, so that's dividing complex numbers in rectangular form. Here's a second one here that I've done. So can you please try this on your own, the top one, before you look at the answer? Okay, so just pause where you are, try the question. Now I'm going to go through the answer. So you're going to multiply the top by 2 take away J5, multiply the bottom by 2 take away J5, just because it's a complex conjugate of the bottom. So you multiply your brackets. 3 times 2 is 6, 3 times negative J5 is negative J15. Negative J2 multiplied by 2 is negative J4, negative J2 multiplied by negative J5 is plus J squared 10. The bottom bit is a complex number multiplied by its complex conjugate, so it's just the first squared plus the second squared. And that's always a plus in there, by the way, it's never a takeaway. Doesn't matter if that number in there is negative, because it doesn't matter, it's just all the way around. Right, then you simplify the top bit by putting in -1 for J squared, and you split your fraction and you get -4 over 29 take away J 19 over 29. Okay, now the next bit is all on the different forms of a complex number. Now the way that we've been looking at them so far is rectangular, and it looks like this. You see the real axis and the imaginary axis. The real part tells you how far along this line it is, and the imaginary axis tells you how far up this line it is. So a complex number always looks like that. But sometimes that's not what we're looking for. Sometimes we would rather know the length of the line, the length of the complex number, its magnitude, and the angle it makes with the positive x-axis. This is the positive x-axis, and angle is always measured from here. Now, key things, your angle is always got, that should be theta actually rather than x. Change that. Right, so theta, your angle there, has always got to be between 180 degrees and negative 180 degrees and 180 degrees, which in radians is between negative pi and pi radians. So this is rectangular form. This is, I suppose you can think of this as normal form if you wanted. I don't really think of that, but that's the way you might have it in your head. And this is polar form. Now polar form is actually really useful because it allows us to turn and move things through a different number of angles and all that kind of stuff. It's actually really useful in comparison to rectangular form. Now this is the long form polar form, and we don't really use it. The only reason we would ever see this formula written here is when we're going back to rectangular form. But that's the key there. That's what polar form looks like, that's what rectangular form looks like, and this is what their argand diagrams look like. And the other key message is that the angle has to be between negative 180 degrees and 180 degrees, or negative pi and pi radians. In Engineering Maths 4, which this is, we use radians a lot more than we use degrees. So get used to using radians, just get used to dealing with it in your calculator. I'll show you the different things that we need to do involving radians and examples and in the revision sheets. Right, so what I'm going to do is converting from rectangular to polar. This is one of the most important things that we did in Engineering 1 in terms of what it's going to help us with in the future. So the first thing you always do is you sketch an Argand diagram. Now, this is very similar to your CAST diagram that you'll have seen when you're doing solving trig equations basically, but because we're working between negative 180 and 180, the quadrants look slightly different. So we sketch a diagram and tick the right quadrant for it to be in. Then our first formula, the magnitude or the length of our complex number, is just the square root of x squared plus y squared. Then part 3, your angle is the inverse tan of y of your complex number divided by x of your complex number, remembering that if either of these are negative, you don't put that into your calculator, you just type it in as a positive. Right? And then you express as z equals r at an angle of theta. And that angle, we need to make sure that we look back and we use this part here. Right, so what I'm going to do is, as I said, because this is slightly more difficult, I'm going to run through it. I'm actually going to write this rather than just talking you through it. I'll do a couple of examples of this. As I said, it shouldn't be new to you, but I want to make sure that you remember how to do it. So, now in this code, as I showed you in Engineering 1, there is buttons on your Casio calculator that will do this for you. However, you need to show the full working every single time you change from rectangular to polar or polar to rectangular. You can't just type it into your calculator. You can use the calculator to make sure, but you must show the full working. Right, here we go. So first thing is you draw a wee rubbish diagram. Now my diagram is going to be awful because my wee thing that I'm drawing this on is rubbish, right? Right, so it's 3 along the way, so that's that way, and 7 up the way. So my complex numbers in that there, and that for this quadrant I just do leave the angle the same, it just stays at theta. Right, so then we say z equals, remember your formula is x plus jy, so z is equal to the square root of x squared, so 3 squared plus 7 squared. So take that into your calculator. And that gives me the square root of 58, or 7.62. So I'm just going to write it 7.62. Right, so theta, then theta equals the inverse tan of y over x. So theta equals inverse tan of 7 over 3. Type that into your calculator, and I get, and I'm going to do this one in degrees, right? I should have said that at the start. Which gives me 66.80. Okay, so then, why have I put Z there? It should be R. You chit. Right, it should be R there, sorry. Right, so then your complex number is Z equals R at an angle of theta. So we have 7.62 at an angle of, then we need to look at our diagram. Well, this tells us we keep the angle the same, so that's 66.80 degrees. And there we go. And remember the POL button in your calculator allows you to do that. But remember, you need to put a comma between your 3 and your 7, and to get your comma, you press Shift and then your wee close bracket button, like that. That allows you to check your answer, as I've said before. Right, so have a wee practice at that maybe. Right, example 2. And last time I suppose we'll do radians. Right, so Z equals 4 take away J 9. Right, so first things first. We get a diagram, we don't even need to write M and real on it, right? It's just for us, right? So 4 along would be that way, and 9 down the way would be so it would look like that, a complex number. And remember, my table is theta, if it's in radians, pi take away theta, negative pi plus theta, and this angle in here is negative theta. So that's in this. So my complex number is in this quadrant. So whatever I get is my angle. I'm going to make it the negative of it. Right. So r equals the square root of 4 squared plus negative 9 squared. Which gives me square root of 97 or 9.85. Okay. Then here, theta is the inverse tan of y over x, so that's negative 9 over 4. Now remembering, this never goes in as a negative. This diagram here sorts out that negative. So when you're typing that in, you're just typing that in as 9 over 4, right? Negative never goes into inverse cos, inverse sine, or inverse tan, right? So I'm just typing that in as the inverse tan of 9 divided by 4. Make sure my calculator's in radians this time. Which gives me 1.15. Okay, so Z equals 9.85 at an angle of, it's 1.15, but it's negative 1.15. Like that. I'll just do one more example just to make sure everything is all fine. So express in polar form again, and this time in radians. Z equals negative 12 plus J7. Right. So step 1, we draw a wee diagram to make sure that we get an angle right. So negative 12 would be down here, and 7, what would be up here? So our complex number looks like that. So remember, that's theta, negative pi plus theta, and pi take away theta. So that means whatever I get for my angle theta, I do pi take away that to get my answer. Right. So r equals square root of negative 12 squared plus 7 squared. And my writing's starting to go to pot now. That's the square root of 193, which is 13.89. Theta equals the inverse tan of 7 divided by negative 12. But again, that negative goes in as a positive. So I've got the inverse tan of 7 divided by 12, which is 0.53. So then Z equals 13.89 at an angle of, well, it's pi takeaway. So I've got 13.89 at an angle of 2.61 rads. And that's me done. So that's a reminder of a Maclaurin series question. That's me going through everything in complex numbers, pretty much. Apart from, I've got to go from polar back to rectangular in the next lecture, and then there's the new stuff in the complex numbers. Now the new stuff is not tricky, right? It looks difficult, but it's not difficult. So just make sure you watch the videos, and if you get any questions, please ask me. Hope everyone's well. If anyone's got any questions about this stuff, and has got any questions about how we're progressing, basically we've got the opportunity to get this maths done this year. Because if you don't do it this year, we're going to have to do it next year at uni, which puts an extra class in your timetable. So I think it's better if we get it done now. It gives you more time to concentrate on your other subjects when you get to Strathclyde next year. Okay.